Hey guys, I'm Keenan Castro,
I'm Katie Long.
and our team is called the KatsuControllers.
Our project, the GoPro, is a smart plant care mechatronic system that ensures the well-being of indoor plants and reduces the problems that first-time plant owners face.
First, they no longer have to keep track of the amount of moisture that is required for each and every type of plant. There's a lot of different types of plants for first-time plant owners to take care of, so it can be very difficult for them to be able to understand and track which plant requires which amount of moisture. Our system is able to take care of that by being able to differentiate between different types of plants. Second, it's important to ensure that the plant is neither underwatered nor overwatered, as it can significantly hinder the growth and development of the plant. Our system is able to ensure that the plant is watered at its specified soil moisture level, solving this problem.
We set a budget for our project to be $150, as our target audience would be first-time plant owners or plant hobbyists, so we needed to make our design relatively affordable if people were to buy it. Our budget of $150 influenced other design specifications for our project, and we had to resort to the cheapest materials available. The budget was a limiting factor for our total build volume of our project. The material used to create the external housing of our project was acrylic, which is a relatively expensive material, so we had to be conservative with our build volume. We determined that a build volume of 10 by 6 by 12 inches would provide enough room to fit all our components while having enough money for other components. During the initial planning for our project, we needed to ensure that our project could not overwater a plant, so we determined that a small volume of water had to be dispensed to the plant pot at a time to allow the water to evenly distribute into the soil before being watered again. A water pump that could dispense 10 milliliters in a span of 1 second to the plant pot was desired, resulting in a required flow rate of 10 milliliters per second for our pump. Our design is meant to be in small areas such as small desks or on shelves, so we wanted our overall design to be lightweight. Our desired weight for our project is to be under 10 pounds without the plant and a filled water tank to make it easy for transporting the device to different locations within a house. The general functions we wanted our project to achieve were to be able to differentiate between plants requiring different moisture content levels, measure changes in the soil moisture levels, and measure the changes of the water surface level in the tank reservoir.
For the system block diagram, we have defined 4 different types of subsystems. The first subsystem is defined as the microcontroller subsystem, which of course consists of the NR52840 microcontroller and its respective 5-volt power bank. And essentially, this subsystem is responsible for being the brains of the entire mechatronic system, as it takes in information from various sensors and outputs the instructions to whatever other subsystem depending on the state of the state machine. The second subsystem that can be defined is the sensor subsystem, which consists of 3 different sensors used in our mechatronic system: the ultrasonic sensor, the color sensor, and the soil moisture sensor. And essentially, this provides the microcontroller subsystem with the respective readings and appropriate information to allow the microcontroller to process that information to determine what events should be taken next, and action should be taken next in the state machine. The third subsystem we can define is the motor actuation subsystem, which, as you can see on the bottom left corner of the diagram, we have a 3-volt power supply powering a Darlington IC chip, which is used to power the 3-volt DC water pump. And essentially, like its name implies, it takes in information from the microcontroller subsystem to determine when to actuate the water pump to provide the plant with the proper amount of moisture. For the fourth subsystem we defined, it is called the user interface subsystem, where, as we can start from the top right corner, we have a green, yellow, and red LED being controlled by a Darlington IC chip, which is powered by a 6-volt power supply. And the purpose of the LEDs is to provide the user with a quick visual indication of the state of the water tank with regard to the water surface level. In addition, we also have an 16 by 2 LCD display, which is connected to an I2C SPI LCD backpack, which is used to provide the user with information regarding the current actions that are being taken place in the system, as well as the respective readings on the sensor subsystem. In addition, we also have the Interact Wing piezoelectric speaker being utilized to provide the user with auditory indication that the water tank is in a dangerous level and needs to be refilled as soon as possible. And finally, we have a simple toggle switch that can be enacted by the user in case that they want to switch to plants that is within our system. Initially, the system will start off in the detect color state, where it'll utilize the RGB color sensor to determine if a plant with an appropriate color patch placed underneath is actually placed within our system. And just a general reminder, for our system we defined red, green, and blue colors as 20%, 40%, and 60% minimum moisture levels. Once the appropriate color has been sensed by the color sensor, the state will define the minimum moisture level threshold that will be utilized as a reference later on in the functionality of the system. And then it will transition into the insert moisture sensor state. The machine will move forward in the state machine and transition into the check water tank state once the moisture sensor has been detected to be inserted into the plant soil. The purpose of the state is to provide the user with their own independent ability to insert the moisture sensor into the plant soil so that they're not under the influence of any external timer when inserting it. Once it's in the check water tank state, 3 options are available for the state machine depending on the input from various sensors. The system will first check if the user enacted the toggle switch on the front panel to indicate that they wish to switch out the plant. If the switch is turned on, the system will return back to the detect color state, where it will reinitialize the system and provide the user with enough time to switch out their plant as desired. In the case that the user does not want to switch out the plant, the ultrasonic sensor will send readings to the microcontroller to determine if the water tank reservoir is above its 20% capacity. In the case that it is, the state machine will transition into the check moisture sensor state, which is essentially kickstarting the entire process for determining whether to actuate the water pump or not, depending on the moisture level of the plant itself. In the case that the microcontroller determines that the water tank is below its 20% capacity, as indicated by the ultrasonic sensor readings, the system will transition into the refill tank state, where essentially the user is to refill the water tank up to at least 100% capacity in order to transition into the check moisture sensor state. Once it's in the check moisture sensor state, the soil moisture sensor will be utilized to determine if the current moisture level of the plant is above or below the defined minimum moisture level as indicated earlier in the state machine. In the case that the current moisture level is above the minimum moisture level, the state machine will revert back into the check water tank state, as the water pump does not need to be actuated to provide moisture to the plant itself. In the case that the current moisture level is below the minimum moisture level, the state machine will transition into the actuate water pump state, where it will actuate the water pump for 1 second and then start a timer for 30 seconds to allow the water to distribute evenly throughout the plant. And once the timer runs out, the state machine will transition from the actuate water pump state and return into the check water tank state to start the entire process all over again. Here we can see the general circuit schematic for a mechatronic system. Out of all the sensors, the ultrasonic sensor requires a 5-volt input, while the rest of the sensors only require 3 volts. For interfacing to the LCD module, it is connected from the NRF to the I2C SPI LCD backpack. We can see that the purpose of the backpack is to reduce the number of pins required to power the LCD display from 16 pins to 3 pins for I2C communication with the microcontroller. It is also important to note that 2 Darlington IC chips are utilized to power both the 3-volt DC water pump and the 3 LEDs, since the required current to run both components is greater than a 4 mA maximum current rating for any of the pins on the microcontroller. In addition, the reading from the echo pin on the ultrasonic sensor needs to be brought down from 5 volts to 2.5 volts using a voltage divider through R1 and R2 in order to process the voltage readings to a level below the maximum voltage limit for any pin on the microcontroller.
With the NRF microcontroller, the main components used in our project are a capacitive moisture sensor, an RGB color sensor, an ultrasonic sensor, and a water pump. From semi-moist to very moist, the stickers colored red, green, and blue are stuck on the bottom of the plant's pot. The plant would then be placed on a platform directly above an RGB color sensor. Once the color sensor identifies one of the 3 colors, and the moisture sensor has been inserted into the soil, the microcontroller will take moisture readings of the soil and compare them to moisture values for the specific color. The colors red, green, and blue correspond to 20, 40, and 60% moisture needed in the soil. These moisture percentages were obtained through prior testing with a capacitive moisture sensor. If the moisture content of the plant exceeds the limit, then the microcontroller will continue to monitor the soil until it reaches below the limit. Once this happens, the water level of the tank adjacent to the plant is measured by an ultrasonic sensor. The water level of the tank will be indicated by 3 LEDs, green, yellow, and red. As long as the water level of the tank is slightly above the water pump in the tank, the pump will deliver water to the plant for 1 second and then wait for 30 seconds for the water to distribute evenly into the soil. This will cycle repeatedly until the required moisture level is reached. If the water level is close to the pump will stop and the NRF will start to play a noise along with a blinking red LED to indicate that the tank needs to be refilled with water before pumping more water.
Here we're demonstrating the use of a toggle switch on the front panel to provide the user with the ability to switch between different plants in our system. Here's a quick demonstration of the ultrasonic sensor providing accurate readings as we refill the water tank reservoir with water accordingly. To validate our preliminary design specifications, we perform small experiments and basic measurements. From the top table, we can see that we were able to satisfy the specifications and requirements for the spatial volume, the build weight, and the pump flow rate. Although we were unable to satisfy our maximum budget limit, as the total cost of the final system was nearly $200. With regard to validating our desired functionalities, we were able to perform further experiments with the sensors to ensure that they are able to be utilized properly and as expected. As you can see, we were able to validate that the appropriate sensors were able to be used for their respective functionality.
Most of the concepts that were applied to this project were taught in the mechatronics course, such as using a Darlington IC to drive multiple LEDs and implementing state machines for our project. One important lesson that we learned was we couldn't use a voltage divider to drive our water pump because it couldn't provide enough current.
If we had more time, we provide the user with a much more robust user interface by allowing them to be able to save their own color and moisture level profiles. And we'd probably use the LCD screen and possibly a rotary encoder to allow this ability to happen. Second, we'd look into completely separating the electronic components from the primary space for the plant base, and the water tank, as this would significantly reduce the hazard of water damage to the actual components.
My contributions to this mechatronic project were the microcontroller subsystem, the motor actuation subsystem, and the fabrication process of our project. For the microcontroller subsystem, I discovered that a special portable charger with the always-on function needed to be purchased as the microcontroller did not draw enough current to keep a normal portable charger on. I also designated most of the pin locations for our sensors based on the functionalities of each pin. For the motor actuation subsystem, I initially created a physical circuit that would power the 3-volt water pump with a 6-volt power supply using a voltage divider consisting of two 680 ohm resistors, but we discovered the pump could not draw enough current from the voltage divider. Instead, we had to use a separate 3-volt power supply to power the pump. I also fabricated the external housing and the water tank of this project using acrylic sourced from a plastics vendor. I also made further modifications to the project to accommodate our components. From this project, I've learned that acrylic is a difficult material to work with in terms of cutting the material, since it is brittle and can be easily scratched. I've also learned that the water pump used in this project can be easily clogged by debris, so a filter would be needed at the pump inlet. Future recommendations for this project would be to use polycarbonate for the external housing, as it does not crack during cutting, but it deforms instead.
For myself, I was able to contribute a fair and equal amount to the project. For the subsystems, I was responsible for acquiring and retrieving the appropriate signals from each of the 3 sensors that were utilized in order for the microcontroller to process information, and I was also responsible for designing a friendly user interface that would provide the user with useful information regarding the state of the system. I was also responsible for leading the development of the state machine that was used in our system, as well as developing the overall circuit schematic within a program called EasyEDA. Overall, there are 3 learning points that I obtained as a result of this project. The first is to never assume that the sensors will work in their specific context, so it's important to always test their limitations as soon as possible. Second, debugging is a tedious and time-consuming process, so one must ensure that there is enough time within the design process for fixing code and other problems. Finally, it's also important to never focus on one sensor or actuator at a time. In our case, we were unable to dedicate a large amount of time for exploring and testing these components, but it is definitely required in the future for larger projects.
This concludes our presentation for our mechatronics project.
Thanks for watching, and we hope you enjoyed it.